In chapter 2, we're going to discuss the relationship between functions and their graphs. So in 2.1, what we're going to do is we're going to look at some basic graphs and discuss symmetry. But first, we're going to start with this idea of continuous. Now, when we talk about a continuous function, that will be formally defined in calculus. So in pre-calculus, when we look at a continuous function, all we're really saying is if you can draw the graph without lifting your pencil from the paper, then it's continuous. So let's look at these two graphs. Notice that if I look at this first graph, from start to finish, I can draw it without lifting my pen. But in the second graph, I can't because there's this break. So I have to lift and then come back and draw, which means in this first graph, this would be an example of a continuous function. And the second graph would be not continuous. So instead of saying not continuous, what we say is it's discontinuous. Again, you will explore this more. Well, that looks like a weird OUS. You will explore this more in calculus. Let's move on and look at this idea of increasing, decreasing, and constant functions. So when you want to decide whether a function is increasing, decreasing, or constant, what you want to do is look at the graph as you go from left to right, or as the x values go from x to right. So as you go from left to right, is the graph going up or down, or is it just remaining the same? A graph is increasing if it rises as you go left to right, or it goes up. Formally, using math symbols, what that says is that whenever the x values go from small to large, so that is what this x sub 1 less than x sub 2 means. It says when the x values are going small to large, or in other words, going from left to right, if the y values are also going from small to large, or getting larger as we go from left to right, then it's increasing. But don't worry too much about that notation. You just want to look at the basic idea. So decreasing would just be that the graph falls as you go from left to right. Mathematically, what that's saying is if your x values are going small to large, or left to right, but your y values are going from large to small, then it's decreasing. If the function is constant, then your graph will remain the same as you go from left to right. So again, mathematically, that's saying as your x values go from small to large, or left to right, the y values remain the same. Let's look at what that means in this sample graph. Notice that as I go from left to right along my x values, this graph, now don't get confused by the arrow that's pointing up. As we go from left to right, the graph is actually going down. This would be an example of decreasing. Now, when we say it's decreasing, we're going to list the interval of x values. So this function is decreasing from negative infinity, and that's an x value. And then it's going to be decreasing till an x value of 1. When we talk about intervals of increasing, decreasing, or constant, they're going to be open intervals with parentheses. Okay, so at 1, it stops decreasing, and then from x is equal to 1 to 3, notice that the graph is going up, it's rising. In this case, we say that it's increasing. And the interval that it's increasing on, again, these are x values, would be x equal to 1 to x equal to 3 with parentheses. And then as we move on to x values that are larger than 3, we see that the graph remains constant. And this graph is going to remain constant until it gets closer and closer to infinity, which means this is constant on the interval from, in parentheses, 3 to infinity. Example 1, we have a graph, and we want to list the intervals where the function is increasing, decreasing, and constant. So remember, as we go from left to right, notice that this function remains constant. So it remains constant from x on the interval from negative infinity to x equal to -1. So that open circle is okay because we're not reaching -1. Remember, this is an open interval. So I would say constant. And I would list the interval from negative infinity to -1. And then at -1, notice that there's a dip here. From -1 to 0, this function is falling, it's decreasing, but it's also going to flip and start going back up at x is equal to 0. So we only get decreasing on the interval from -1 to 0. Again, remember, these are the x values. Okay. So again, this is from -1 to an x value of 0, it's going to decrease. And then if you look at the graph, you can see that it's just going to continue to go up and up and up as we go from left to right, which would mean we're increasing from the x value 0 to positive infinity. So the next thing we want to talk about are some basic graphs that we should all be familiar with. The first graph we're going to look at is down below here. This would be our constant function. And the form of a constant function is f of x equal to some b, where b is just a real number. Now remember that you can always replace the f of x with y. So this would be a function of the form y equal to some b value. In the graph below, we can see that it's passing through 2, so this would be y equal to 2, or f of x equal to 2. When you have a constant function, the domain, so we're going to look at some properties right now, the domain will always be all real numbers, so negative to positive infinity. But the range, the y values, will just be the set that contains the single element b. In the example we have here, the range is just going to be 2, because y is always equal to 2. It's going to be constant, so it doesn't increase or decrease from negative to positive infinity, and it's continuous on its domain. I do not have to lift up the pen when I sketch the graph. We'll look at some more functions. The next function would be the identity function. This identity function is going to be f of x equal to x. Again, remember, you can always replace that f of x with y, and you get the equation y is equal to x. Looking at the graph, we could see that the domain, we get all the x values, and we get all the y values. So the domain and the range are going to be the same. It's going to be negative to positive infinity for both. And this is always increasing. So it's increasing from negative to positive infinity. And again, this one is also continuous on its domain. Another basic function that we use quite a bit is called our squaring function. So the squaring function is f of x equal to x squared. Or again, remember, this would be y equal to x squared. And the domain here, we will get all of our x values. So that domain is going to be negative to positive infinity. But look at the range. We have no y values until we reach 0. And then that would be our first y value. And it's solid, so we include 0 in our range. The range is just going to go from 0 with a bracket because we're including 0 to infinity. And now this function goes down from x equal to negative x equal to negative infinity, sorry, to x is equal to 0. So that's where it's decreasing. But then at 0, it goes back up. So it's going to be increasing from 0 to positive infinity, which is what we have listed to the side here. This function as well is continuous on its domain. The next function we're going to look at is the cubing function. Our cubing function is f of x is equal to x to the third. Now you notice in your textbook, they will have this little thing called an inflection point. An inflection point will become important when we're in calculus. But basically what an inflection point is when a graph switches to being curving sort of downward to curving upward. So if you look at this graph, you see that as we go from bottom up, it starts looking like a curving sort of like an N. If we continued on, it would look like an N. And then it stops at 0 and it changes and it starts curving upward and looking like a U. Although this is not anything that you would be tested on, it does come up in calculus. So what we call that is its concavity, where when it's like this first part, and it looks kind of like an N, that's what we call concave down. And then there's an inflection, and then it becomes concave up. Okay. Now the domain here is all real numbers. We get all the x's and the ranges as well. This function is always going up as we go left to right, so it's increasing from negative to positive infinity, and it is continuous on its domain. Another important function would be our square root function, f of x equal to the square root of x. And here you see that we're going to have a restricted domain and range. Because of the square root, whatever's underneath cannot be negative. But since it can't be negative under the square root, it also can't be negative outside of the square root, which would be your y values. So our domain here is, now notice we do get 0. It's going to be bracket 0 to infinity. That would be our x's. And then our range would be a bracket with 0 to infinity as well. This function is always increasing from its domain, which again, remember, even though the 0 is included in the domain, when we do intervals of increasing, decreasing, or constant, it's always parentheses. So it's going to be 0 to infinity with parentheses. And it's also continuous on its domain, meaning that the graph won't cover the whole rectangular coordinate system, but I still only need to have my pencil trace the graph once without lifting up. And we have a couple more graphs to look at that are common graphs. This next one is our cube root function, so similar to the square root function, except for index or root is 3. Now remember, with a cube root, we are allowed to have negative values, which is why in this particular graph, we don't just get the right-hand side where all the x's are positive and the y's are positive. We also get on the left where the x's can be negative and the y's can also be negative. Our domain is going to be all real numbers. We get all our x's, but we also get all our y's. It is always increasing. So from negative to positive infinity, and it's continuous on its domain. The last function that we're going to look at is our absolute value function. F of x is equal to the absolute value of x. So an absolute value of function actually has two definitions, which is what's off to the side here. If x is greater than or equal to 0, so that would be this right-hand side of the graph, then whatever x you put in is the same x that comes back out, so the y value is x. If x is less than 0, which would be the left-hand side of this graph, then if you put in a negative x, you have to take its negative. So you take the negative of your negative x, and that becomes a positive y value. It sounds a little weird, so let me show you what I mean here. Let's just say that we put in x is equal to 2. Well, that would be greater than or equal to 0, so that means our f of x, or our y value, is equal to that x value of 2. So that would be this point on the graph, 2, 2. However, let's say that you put in an x value of negative 2. Then our y value is going to equal the negative of negative 2, which is positive 2. So at negative 2, we get a y value of positive 2. And that's actually the formal definition of an absolute value of function. Now, this is an example of what we call a piecewise function. Because to properly define it, we have to write it in pieces. In this particular graph, there are 2 pieces. Well, let's go ahead and move on and look at the properties. The domain, we get all of the x's, so that would be negative to positive infinity, and I don't like that color. I want green. I know I'm weird. So negative to positive infinity. The range, now look, our first y value is y equal to 0, so it's 0 to infinity. It's going to be decreasing or going down from negative infinity to 0, but then it starts increasing and going up from 0 to infinity. And this function is also continuous on its domain. So now that we've talked about some basic functions that kind of show up a lot, what we're going to do next is talk about symmetry, because sometimes graphs have symmetry, and if you're graphing by hand and you know there's symmetry, that would mean that you have to plot less points, because you can use symmetry to help you out with your graphing. So the first type of symmetry we're going to look at is symmetry with respect to the y-axis. So when we talk about symmetry with respect to the y-axis, we call that an even function. Okay, so even functions have symmetry with respect to the y-axis. And all that means is if you look at the y-axis, on either side you will have a graph that mirrors itself. So let's go back to this absolute value graph. Absolute value has symmetry with respect to the y-axis. Because if you notice that the graph on the right-hand side, if you flip it over the y-axis, you get the exact same graph on the left-hand side. Imagine folding a paper along the y-axis. The graph has to match up on both sides. So that's an example of an even function, symmetry with respect to the y-axis. Now, when we look at this mathematically, what we're saying is if we put in a negative x value, it's going to be equal the same as if we put in a positive x value. And we saw that with this absolute value function graph, right? Remember, I put in positive x value of 2, and I got the y value of 2. I put in a negative x value of 2, and I got a positive y value of 2. So in this case, whether I put in negative 2 or positive 2, the y values were equal. Let's move on to the next type of symmetry, and that would be symmetry with respect to the origin. I don't like the blue. Why did it do that? So when we talk about symmetry with respect to the origin, that's a little bit more difficult to visualize. But if a function does have symmetry with respect to the origin, we say it's an odd function. An example of that would be this cube root function. This has symmetry about the origin. Now, how you check that is imagine that you took your graph. Let's say I look at the right-hand side and I rotate it around 180 degrees. It's going to match up to that left-hand side. So basically, if you can take the graph and rotate it 180 degrees and the graph is still the same, then it has symmetry about the origin. Again, I know this is a little bit harder to visualize. Basically, symmetry about the origin says mathematically that if you put in a negative x value, it's going to be equal to the negative y value. And let's see if we can go back up to this graph. So for example, in our cube root function, let's just say that I was looking at f of negative 8. So f of negative 8, if we look at this negative value, corresponds to a y value of 2, or negative 2, sorry. Now, if we look at negative f of positive 8, so I'm taking the negative from inside the parentheses and I'm pulling it outside. So we're going to positive 8, and we're looking at the value that corresponds to that. That would be a positive 2, but remember that we had the negative on the outside, so that is also a negative 2. So if putting the negative on the inside or putting the negative on the outside still has the same y value, then this would be a function that is odd, and it has symmetry with respect to the origin. The last type of symmetry that we're going to look at is symmetry with respect to the x-axis. Now, when we talk about symmetry with respect to the x-axis, there is only one function that has that. So if there is symmetry with respect to the x-axis, most likely it's not a function. Okay, so the only function that has symmetry with respect to the x-axis would be f of x is equal to 0. So let me just do a quick sketch of an x and y axis. When we talk about f of x equal to 0, that would be y equal to 0. The graph of y equal to 0 is the x-axis. So symmetry with respect to the x-axis means that when you flip across the x-axis, you get the same graph. Since y equal to 0 is the x-axis, when we flip it, we get the same graph. We get the x-axis. So what I would like to do is go over an example to a function that does have symmetry with respect to the x-axis. But let's look at what this means mathematically. All it means that if you replace y with negative y, you get the same equation, which would mean that you would get the same graph. In example 2, we want to graph this equation. It's not a function. X equal to y squared, and we're just going to plot some points. So I'm going to need to plot a lot of points. I don't want green, I want blue. So why don't I start with x equal to 0, and then I'll get y equal to 0, and this passes through the origin. Now, this is interesting. In this equation, the y is squared, but the x is not. So whenever you have something that's squared and another value that's not, it's easiest to put the values into the squared value. So for example, if I put in y equal to 1 and I square it, I get x is equal to 1. If I put y equal to negative 1 and I square it, I get x is equal to 1. So I'm going to pass through the point 1, 1 and the point 1, negative 1. If I put negative 2 in for y, I get a positive 4 for my x value. So it's going to pass through 4, -2. If I put in a positive value for y, I get 4 for x. So it's going to pass through 4, +2. This graph, and I don't know if you're familiar with it, is the graph of a parabola that opens sideways. Notice it does have symmetry about the x-axis, because if I were to fold this graph along the x-axis, the two sides would match up. However, something to note is this is not a function. So remember, a function needs to pass the vertical line test, meaning if I can draw a vertical line that passes through 2 or more points, it's not a function. I can draw a vertical line that passes through 2 points. So this is an example where it's not a function. And in fact, again, like I said, if a graph does have symmetry with respect to the x-axis, most likely it's not a function, it's actually just an equation. Well, what happens if you don't have a graph and instead you have an equation and you want to decide whether a function is even, odd, or neither? Okay. Well, we do this algebraically. First thing I'm going to check is I'm going to check if the function is even. So remember, even just means that f of x and f of -x are the same. So I know in part A what f of x is. It's equal to 0. So what if I put in -x into my function? Well, it's still equal to 0 because this is the constant function y equal to 0. It doesn't matter what you put in for x, y is always going to be equal to 0. So because f of x is equal to f of -x, this is an even function. Okay, so again, f of x equal to f of -x means it's even. Well, what about odd? To show odd, you have to show that f of -x is equal to negative f of x. Well, negative f of x is equal to, in this particular case, -0, which is equal to 0. So notice that if I compare f of -x to negative f of x, I get the same answer. I get 0. These guys are equal. So f of -x is equal to negative f of x, and this is an odd function. Usually, if we're dealing with functions, if it's even, it's not odd. If it's odd, it's not even. But remember, this y equal to 0 is that special case where it's actually a function, but it has symmetry about the x-axis. It also has symmetry about the y-axis, and it also has symmetry about the origin. It has it all. Let's try this again in part B. So I always check even first. I always check even first because I already know what f of x is. It's given to me. In part B, f of x is equal to the square root of x plus 1, which means I'm going to compute f of -x and see if I get the same thing. Well, that means that underneath the square root, I replace x with -x. And there's nothing I can do to get these two to look the same. So this is not even. So if I could do something algebraically to make this look like square root of x plus 1, then it would be even, but cannot. Okay. So I know that f of x is not equal to f of -x, which means it's not even. But now what about odd? I have to show that f of -x is equal to negative f of x. And I already have f of -x listed. I now just have to compute negative f of x and compare them. So negative f of x says we're going to put the negative on the outside of this function, x plus 1. Now, is there anything I can do to get f of -x and negative f of x to look the same? And the answer is no. So since f of -x is not equal to negative f of x, sorry, This is not odd. So not even, not odd, it must be neither. So it's even, it's odd, or it's neither. In C, we have f of x equal to x minus 1 over x. Again, the first thing I'm going to check is it even? So I want to compute f of negative x. F of negative x would be negative x minus 1 over negative x. So again, wherever I see x, I'm just replacing it with negative x. That means that f of negative x is equal to negative x plus 1 over x. There is nothing I can do to get f of x equal to f of negative x. Since these are not the same, it's not even. Again, it's not even because f of x and f of negative x are not the same. What about odd? So if it's odd, then f of negative x would have to be equal to negative f of x. I've already got f of negative x listed. So what is negative f of x? That means it's going to be a negative of the whole function, which is x minus 1 over x. And if I distribute that negative, I get negative x plus 1 over x, which is exactly f of negative x. So I've shown that f of negative x is equal to negative f of x. And this is odd. Okay, so you guys getting the idea? We have 3 more. D. We have f of x equal to negative x to the third minus x. What is f of negative x? So that's going to be negative, replace the x with negative x to the third minus negative x. So just be careful with all these subtractions. So since negative x to the third power is still negative x because the exponent is odd, then the negatives cancel and I get a positive x to the third, and the minus minus would be a plus x. So f of x is not equal to f of negative x. This is not even. Well, what about negative f of x? Negative f of x says we're going to put a negative around the whole thing. So negative x to the third minus x. And if I distribute that negative, I get x to the third plus x, which is exactly f of negative x. So f of negative x, I'll write it out to remind you, is equal to negative f of x, and we've just shown that this function is odd. 2 more. Part E, we have f of x equal to x to the 6th minus x to the 4th plus x squared. Let's compute f of negative x. That would be negative x to the 6th minus negative x to the 4th plus negative x squared. Since the exponent 6 is even, the negative x to the 6th becomes x to the 6th. Since negative x to the 4th, 4 is even, the negative x to the 4th becomes a positive x to the 4th. So this becomes minus x to the 4th. And the negative x squared becomes a positive x squared, so it's plus x squared. So yes, f of x is equal to f of negative x. And we have an even function. So chances are, if it's even, it's not going to be odd. I'll go ahead and check anyway by computing negative f of x. So I'm just putting a negative around the whole function, which is x to the 6th minus x to the 4th plus x squared. And if I distribute that negative, I get negative x to the 6th plus x to the 4th minus x squared. So again, note that f of negative x is x to the 6th minus x to the 4th plus x squared. So these are not equal, and this is not odd. Last one, we have an absolute value function. So think about this function. F of x equal to the absolute value of negative 3x is also equal to the negative 3 in absolute values times the x in absolute values. And the absolute value of negative 3 is simply 3. Let's compute f of negative x. F of negative x is going to be the absolute value of negative 3 times negative x, which is the absolute value of negative is a positive 3x. And if you pull the 3 out, these are the same. So f of x and f of negative x are the same. This is an even function. So sometimes you just got to play around with it. I know it's not going to be odd, but I'm going to check anyway. What about negative f of x? So negative on the outside of the absolute value. Now I'm going to try to get it to look like f of negative x, but I don't think I can. The negative on the inside of the absolute value will turn to positive, but the negative on the outside is still there. So this is actually negative 3 to the absolute value times the absolute value of x. I can't get f of negative x and negative f of x to look the same, so this is not odd. And I knew it wouldn't be odd because it was even. And remember, most functions that are even would not be odd. Okay, so this is it for this section.